Hi guys, in this video I'm kind of gonna help you understand some of the questions on induction quickly, also the other parts of algebra. So what I'm gonna do is see that most of the times the questions that are asked from inductions are related to divisibility, proving the inequalities, and maybe forming the conjectures. So what I'm going to do is I'm going to kind of quickly take 3-4 examples of overall all the topics in induction. So the first type is the divisibility one. Use the method of induction to prove 5 to the power 2n minus 24n minus 1 is divisible by 576. So without any delay, I know that your time is really important at this moment. So what I do is I'm kind of going to straight away start the procedure. So I have to prove that 5 to the power 2n minus 24n minus 1 is divisible by 576 for all real positive or positive integers. That's my question. Alright, so what I'm going to straight away start with is that first of all you take n equals to 1. Let's try to prove n equals to 1 is true. So when you do that, you get 25 minus, because you take n as 1, 25 minus 24 minus 1 over 576, which is going to be 0 over 576, which is 0, which is an integer. So that is so n equals to 1 is true. Now you straight away start with n equals to k. So when you do n equals to k, so it becomes 5 to the power 2k minus 24k minus 1 over 576. This should be an integer. Let's say I'm assuming the integer p, if it is divisible. So assume that this is true. This is assuming that's true. Now using this, I'm going to prove my n equals to k plus 1. So when you take n equals to k plus 1, ideally what I should get is 5 to the power of 2k plus 2, because if you replace k with k plus 1, it's going to be, if you open the bracket, that's going to become 2k plus 2. And this is going to become minus 24 k plus 1 minus 1 over 576. Now this should be an integer. That's what I have to prove. Okay, I cannot just directly say that it's going to be integer, so I have to use my pk statement. So see, generally what you should do is, while you're using divisibility, make one other thing as subject, like either 24k as subject and plug out here, or make 5 to the power 2k as subject. So 5 to the power 2k equals to 24k positive 1 plus 576p. So 576p, and then bring other thing this side. Now this is what I'm going to use. So what you do is 5 to the power 2k into 25 minus 24k minus 24 minus 1 over 576. Now plug this value out here. So when you do that, what you get is 25 times 24k plus 1 plus 576p minus 24k, this is as it is, minus 25 or 576. Now 24 into 25 is you can write down, and if you simplify with this k, it's going to be 576k plus 25 plus 25 times 576 p and minus 25. So this is going to cancel, and you're going to get 576. Now if you simplify this, it's going to be 576 can be taken common, and it'll become k times 25p, which is 576. Now this cancel out, so we get k plus 25p. Now as out here k is an integer and your p is an integer, so this answer is going to be an integer. So as your inequalities, do not forget to write on the step n equals to 1 is true for n equals to 1, n equals to k, n equals to k plus 1. It's going to be true for n belongs to z positive. Here is the next question. So in this example, we have to prove using induction. This again May 16 question. You have to prove using induction that n times n squared plus 5 is divisible by 6. So taking the example, taking similar route as the earlier example, it's going to be n times n squared plus 5 over 6. This should be an integer. So this is what is my aim to prove, and that should be, this is true for all n belongs to positive real positive integers. That's what I have to prove, where n belongs to z positive. So what I do is I take n equals to 1. So when I take n equals to 1, so it's 1 times 1 square plus 5 over 6, which is going to be 6 over 6, which is 1, which is divisible, so it's true. Alright, now take for n equals to k. Assume n equals to k is true. Assume n equals to k is true. So it's going to be k times k square plus 5 over 6 equals to, let's say, integer p. Alright, so that's what up to, that's I'm assuming. So it's going to be k cubed plus 5k equals to 6p. Now, this is what is the most important step. Until unless I use n equals to k to prove n equals to k plus 1, your inequality will be incorrect. So let's say now you try for n equals to k plus 1. So when you try with n equals to k plus 1, it's going to be k plus 1 times k plus 1 the whole square plus 5. Alright, so if you expand this, it's gonna become k plus 1 k square plus 2k plus 1 plus 5 over this is gonna be 6 and 6. So now it's, if I take k plus, open up the bracket, so if I take k plus 1 k square plus 3k plus 6 2k plus 6 over 6. Now you open up the bracket, it's gonna become k cube plus this is gonna become k cube plus 2k plus 6k. This is gonna be 2k square plus 6k plus k square plus 2k plus 6 over 6. So k cube plus you're gonna get out here k cube plus alright, so this is k cube plus 3k square plus 6 plus 2 is 8k plus 6 over 6. Okay, so now here is a little problem because I cannot see clearly what I'm going to use out here. So now this step, after this step, what I'm going to do is I'm going to take k cube plus split this 8k as 5k plus 3k and plus 3k square plus 6 over 6. Now I can pair up this number, and this alone. As I know that if I isolate this k cube plus 5k over 6, I know that this is divisible by 6. Okay, and the value in fact is p. And now the next target is to prove this one. So 3k and k plus 1 if I take common over 6, and 6 over 6 is 1. So this number, if you take any k number, like any, for example, if you take k as 1 into 2, which is 2, 2 into 3 is 6, 6 divided by 6 is integer. K equals to 2, if I take 2 in 2 plus 1 is 3, 3 into 2 is 6 again. So this is going to be divisible by 6 as well. So if this is integer, this is integer, this is integer, which proves that your n cube plus 5n over 6 is gonna be integer for all real numbers. All right, so when I have to write down n equals to, it's n equals to 1, n equals to 2, n equals to 3, n equals to k, it is gonna be true for all real numbers, true for all positive integers. Next, I'm going to demonstrate one of the induction on trigonometry using complex. So in generally in the complex you have this problem, like, you know, using induction prove that cos theta minus I sine theta to the power n equals to cos n theta negative I sine n theta. Now in the exam most of the students took as positive and they got wrong. So please read the questions carefully. So what I'm going to do is I'm going to prove cos theta plus minus I sine theta raised to n equals to cos n theta minus I sine n theta for all positive integers. So all positive integers. So what I'm going to do is I'm going to quickly take n equals to 1. Take n equals to 1. So cos theta minus I sine theta raised to n raised to 1 is going to be cos theta minus I sine theta, which is going to be true as cos of 1 theta minus I sine of 1 theta, which is cos theta minus I sine theta, which is true. Now let us assume this is true for n equals to k, true for n equals to k. So cos theta minus I sine theta raised to k is gonna be cos k theta minus I sine k theta. Now let's prove for n equals to k plus 1. So if I take LHS, it's gonna be cos theta minus I sine theta raised to k plus 1. So it's gonna be cos theta minus I sine theta times cos theta plus I sine theta raised to k, because I can split k plus 1 into 2 powers. Now from this statement, I can plug, in place of this, I can plug this value. So what I'm going to show now is that I'm going to just kind of take cos theta minus I sine theta raised into cos k theta minus I sine k theta. See, what I want to prove is, the most important is, if I take this thing, my k plus 1 statement will be cos theta minus I sine theta raised to k plus 1. What I should get is this, cos k plus 1 theta minus I sine k plus 1 theta. This is what I should get. Alright, so now if you open up this, you get cos theta times cos k theta minus cos theta times I sine k theta, and minus I sine theta cos k theta, and plus sine theta sine k theta. Now why this became plus is because I times I is going to be I squared, which is going to be negative. So negative, negative, positive, and then again it's going to become negative. Alright, so we get cos theta cos k theta minus sine theta sine k theta, which is going to be, if you remember, cos A plus B is cos A cos B minus sine A sine B. So this is what I'm going to use. So this is cos k theta into cos theta, cos A cos B minus sine A sine B. So it's going to be cos theta plus k theta minus, if I take out, it's going to be cos theta plus cos theta sine k theta plus sine theta cos k theta times I. It's going to be cos, if you take theta common, it's going to be k plus 1 theta minus, this is nothing but sine k plus 1 theta as well. So this comes, because you know that cos A cos B plus sine A sine B is going to be cos A plus B. Alright, so this is, we could prove that it is true for n equals to 1, n equals to k, hence it's going to be true for n equals to k plus 1. True for n equals to k plus 1. Alright, now here's the last type where you have to prove the conjectures for the nth derivative. So this is one of the November 15 paper question. So the question, first one was really easy, like you have to open up using compound angle and show it. So the first part of the question is that I have to prove that sine theta plus pi by 2 equals to cos theta. So what I'm going to do is that I'm going to first of all expand sine theta plus pi by 2 as sine theta cos pi by 2 plus cos pi by 2 cos theta into sine pi by 2. So you can clearly see that cos pi by 2 is 0, so 0 into anything is going to be 0, and sine pi by 2 is 1, so that's going to be cos theta. So that's my first part is proven. Now this is going to be really important identity for you to prove the next part. So the B part is that this is your A part, and B part is that prove by induction that derivative of nth derivative of sine AX is gonna be a to the power n sine AX plus n pi by 2. This is what I have to prove by induction. Now what you have to be really careful about is that you have to make a conjecture out of it. So you have to make sure that you're derivating correctly. So sine AX derivative is cos AX times, so I'm first finding dy by dx, so cos AX times A. Now second derivative is gonna be negative sine ax times a square. Third derivative is gonna be negative cos ax times a cube, and fourth derivative is gonna be d4y, or dx cube is gonna be negative positive sine ax times a cube, a raised to 4. So what we can see is that we can see just the trend between a values very clearly, that it's happening, but I have still not got any idea about what's happening to these negative signs. What do we do with that? Now if you notice, the upper part that they said is that sine pi by 2 plus theta is cos theta. So I'm going to use that property to express all the derivatives purely in terms of sine. So if I could write down this as a times sine of pi by 2 plus ax, because I have written this is my theta, so pi by 2 plus theta. Now just a reminder I'm giving you is, if you notice this property, if you remember those properties, like cos pi by 2 plus theta is like, you know, negative sine theta, and you have sine pi by 2 plus theta properties, which is gonna be cos theta, and so on. So I'm gonna use these properties out here. So if I have negative sine theta, I can write on as cos pi by 2 plus theta. So I have already this as one of the answers, so I can write on this as a square times sine of pi plus ax. So because I'm trying to write on this as, if you want to write on sine as sine, what you do is just add pi to the angle, and you don't have to even worry about this negative sign. If you want to convert sine to cos, then you add pi by 2. Automatically it gives you sine cos, and so on. Now if you want to convert sine into cos again, so that's going to be negative cos, so it's going to be now I have to add pi by 2 to this angle. So a cube sine pi plus pi by 2 plus ax, it's gonna be a cube sine 3 pi by 2 plus ax, and so on. So, and now from sine to sine, you can add up straight away 2 pi. So a cube a to the power 4 sine, like, you know, you can write on 4 pi by 2 times ax plus ax. A little bit smarter in this. You gotta be smarter in this case. So in place of this pi, I could write on 2 pi over 2. So these are the things which will come by practice, not by just like in looking at the video. So what I would do is that if I have to prove, now look at the conjecture, sine, 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 a out here. So my conjecture is a to the power of 4, which is a to the power of, we can say, n sine n pi by 2 plus ax. Now I did so because many of the time here they directly had given the conjecture, but many of the times you have to prove that. All right, so now I'm going to apply induction to prove that this is the nth derivative of my expression. Okay, so nth derivative of expression is going to be, now assume that's true for n equals to 1. So if you plug n equals to 1 out here, automatically you're going to get cos x as the derivative. So if I plug n equals to 1, so dy by dx is going to be a times cos ax. All right, which was the question itself. First derivative you can see. Now true, assume that's true for nth derivative. So kth derivative, dy by dx k equals to a to the power k sine n pi by 2 plus cos n pi by 2 plus ax times a. So what you're going to get is a to the power k plus 1 cos n pi by 2 plus ax. Now I want to convert this to sine, so you just add up sine n pi by 2 plus pi by 2 plus ax. So because you know the sine pi by 2 plus theta is cos theta, so it's going to be a to the power n plus 1 sine n plus 1 over 2 pi plus ax. Now this proves your conjecture, because if you replace n with n plus 1, that's your true statement. So this is your k plus 1th derivative. So your kth derivative is ideally dyk over dxk. Dxk is going to be a to the power of k cos sine n pi by 2 plus ax. So I've kind of proven every single type of questions in induction. Hope this help you to like, you know, solve some of the really good questions on the induction.